At the beginning of our unit on right triangles, we're going to look initially at the connection from our last unit with similarity. In particular, our focus today is entirely on one drawing. With one picture, we will be able to create more similar triangles, and we will see that we can set up and actually figure out a number of segment lengths based on similarity and the geometric mean. In particular, we're going to focus on this. You'll notice the drawing that we have has two main characteristics. First of all, this is already a right triangle. Everything that we're working on today, right triangle, right triangle, right triangle, because this is the beginning of a right triangle unit. Additionally, from that right angle, we've drawn in an altitude. What this theorem is telling us is we actually wind up having three similar triangles. This tiny little triangle is the same shape as the medium, come on, I want yellow here, as the medium size one, and that is still similar to the overall big one. We have three similar triangles. And in every instance, because they are all similar, we know that we can set up proportions based on the matching parts. That's what our focus is on today. Recognizing the matching parts for these three different similar triangles and knowing how to set up the proportions and solve them. That's it. Now, specifically, when we look at these things, the major characteristics that we have to observe, of course, are paying attention to each of the pieces. In every instance, we obviously know that 90 is going to match up with the 90, so that's what we're going to start off with. If we're looking at the overall big triangle right now, the 90-degree angle is going to match up with the 90-degree angle in the medium-sized triangle. Okay, so with this medium, angle D is going to match up with angle C. This is the medium-sized triangle. This is the big triangle. Do you notice in both instances, we have an angle A in both the big triangle and the medium triangle? And of course, that angle has to be congruent to itself, so angle A matches up with angle A. Because of angle, we know that the triangles have to be similar. 90 matches 90, A matches itself. Angle similarity tells us those are similar triangles. Of course, last piece then, in the medium-sized triangle, point C was the last one, and point B is the last one in the big triangle. So that's one piece. Switching colors here, and looking at the small triangle. Hey, one red here. Of course, angle D is 90. So 90 matches 90. In this instance, and I put this one down, D is similar to C for the big one. And then for the small triangle and the overall big triangle, again, they both have angle B. Angle B has to be congruent to itself. So B matches up with B. Again, angle similarity tells us they will be the same or similar. And then that leads us with angle C matching up with angle A. And so we get these being similar. Even though the letters aren't all corresponding and they don't all match up, the purpose of this was just to show you, because of angle similarity, we know that all three of them are similar to each other. It's the same triangle with three different sizes. And so when we look at these pieces, we want to just stop and say, write up the similarity statement for the three pairs? Well, of course, start with any triangle you want. For me, I'm choosing to do the big one, where I'm going to start with my 90 and then go UV. That has to be similar to, if we look at the small one, I put the 90-degree angle first simply because that's always the easiest one to recognize. 90 has to match 90. Z is the 90-degree angle in that small red triangle. In this instance, they're sharing an angle V. And so V has to match V, so position 3 has to match position 3. That leaves me with my third one. Additionally, we need to have the similarity for the median-sized triangle. And in order to do this one, I'm going to match it with triangle WUV at the front. Once again, 90 matches 90, so Z is my 90-degree angle. In this instance, angle U is the shared angle. So I'm going to put it in position 2 to match position 2 up at the front. And then, of course, my last angle is W. This shows us how we can set up our similarity. And I want to point out that, in my opinion, your ability to recognize the similar triangles is the most important skill that we have in this entire lesson. Your ability to recognize this set of similarity is what we can use as a foundation to build any proportions. We can use this as a foundation to actually solve everything. The alternative is to memorize a couple of other theorems. If you want to memorize theorems, you can. I personally think it's easier to have the skill of recognizing the similarity and then use your similarity statements to make the proportions. For at least the way my brain is wired, that's what's easier. We'll look at doing them both ways. There is a piece of vocabulary that actually gets used with this type of picture. And of course, you can just read and see that it's the geometric mean. In your earlier classes, you would have seen that the mean of two numbers, say 10 and 20, in those instances, the mean back then would have meant you add them up and you divide by 2. That would have given you the mean of 15. This is a different one. This kind is actually the arithmetic mean. Essentially, it's the adding mean. We are working on the multiplying mean, which is called the geometric mean. In that instance, if we wanted to get the geometric mean between two numbers like 10 and 20, we would not add them together, we would have to multiply. And instead of dividing, we would have to take a square root. Part of our skills are to simply look at this and say, what is the geometric mean of two numbers 4 and 25? Well, the quick algorithm simply says, take those two numbers and multiply them. What's 4 times 25? 100. After multiplying, you take a square root. So the square root of 100 is just 10. You're done. That's how you get your geometric mean. Where this piece comes from is actually from a proportion. And we are going to see, when we work with this type of picture, we will create proportions from similarity that will look like this. And so the similarity from this triangle, from this picture, leads us to calculating the geometric mean. Knowing how to set up the proportion is the critical skill. Same thing here. What's the geometric mean? Well, if you care about the proportion, the geometric mean is going to be on one diagonal. And then your other two numbers serve as the foundation for it. Cross multiply, x times x gives you x squared. 5 times 30. And please notice what I'm having written down there. To solve it, then you take the square root. This is exactly why I said the steps towards getting the geometric mean are to multiply the two numbers and then take a square root. It's just a shortcut on the amount of writing from cross-multiplying and solving a proportion. Ultimately, it's your choice. When the directions just say find the geometric mean, you can write up the proportion, or you can just cut to the chase and start doing the arithmetic. It's up to you. Both methods are fine. This one, of course, would tell us that 5 times 30 is the square root of, 5 times 30 equals 150. And now we need to simplify this to its simplest radical form. In order to get simplest radical form, we remember that we're searching for the perfect squares that will divide into our number. 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared. Do any of the perfect squares divide into 150, smooth and even? Yes. 25 will divide into 150 evenly. In particular, 150 is 25 times 6. We, of course, had the radical property that said when you are multiplying inside a radical, you can split it up as 2 of them. And this is exactly why we were searching for the perfect squares, because the square root of 25 is something that we know. It's just 5. And so we wind up with our simplest radical form, 5 times the square root of 6, and we're done. Now, of course, we have to also look at how does this geometric mean actually come in and play a role when we're working with this picture. And of course, I mentioned it's because of the similarity. When we look at these pieces, here are a boatload of proportions which we are able to create. And you'll notice in certain instances, for instance here, do you notice how H and H are on one diagonal? H and H, this altitude, is the geometric mean for X and Y. We will be able to use these two pieces to figure out H. That's one of the types of problems that we will be able to do now. Additionally, because of similarity, you'll notice how we've got, I want to change colors here, come on. A and A, how they are on a diagonal. We will be able to use a geometric mean to figure out that length based on having X and C. We can use those two pieces to get A. And likewise, when we look here, we've got B and B on a diagonal. We will have the ability to figure out that length by using Y and C. Each of the things that we do then are going to break down into one of these three cases, and they're based entirely on similarity. Are we pairing similarity with the small triangle? And come on. We can have small similar to medium. That's one type of proportion that we can set up. We can have the medium triangle similar to the big triangle. That's a second type that we would set up. And we can have small being similar to the overall big triangle. And here's where you get some flexibility. You can memorize these three cases. We have them stated as a theorem. Or you can focus instead on understanding how to identify the similar parts and build them as you need them. For me, I think it's easier to look at the pictures and create the proportions, saying small leg matches small leg, hypotenuse matches hypotenuse. That's easier than memorizing all of this. But of course, it is up to you. All of that information is stated right here. Those three equations, based on the geometric mean, can be summarized with these three equations. So, do you choose to have the picture memorized with the three equations, or do you choose to build the proportions based on similarity and just recognizing corresponding parts? That's up to you. Okay, so how are we going to get these three pieces, x, y, and z? Now, frankly, this is actually three separate problems. And when we're working on them, let me start off with some blue. Here's what I'm looking at. When I look at the picture, one of the things that I recognize, I already have two of these pieces. And then I have x right here. Let me put that one down in red. Come on. In looking at the picture, I'm able to recognize our similar triangles for the small red triangle and the medium blue triangle. I'm going to build a proportion based on having the corresponding parts of those. In particular, I know that I've got my small red triangle and I've got my medium blue triangle. In order to match these pieces up, and here I'm going to choose to actually write it out in black, the short leg has to match up with the short leg. So with my red triangle, x is the short leg. What's the short leg in the blue triangle? That's 6. So short leg matches short leg. I also have to match it up long leg with long leg. In my small red triangle, what is the longer leg? Of course, that's 6. Long leg has to match long leg. So in the blue triangle, what's the longer leg? That's 9. And there I've built my proportion. This piece right here is that equation. You can memorize the equation, absolutely valid. I prefer to build the proportion. It's what clicks better for me. Again, you have a choice of memorizing equations or building proportions. Both methods are valid. You just have to be able to do one of them correctly. Now that I've got my proportion built, 9x, 6 times 6 gives me 36. Divide out by 9, and I get x is equal to 4. Awesome. Got that piece. That's one problem. I still have to continue and figure out y. I still have to continue and figure out z. So I'm going to set up a similar type problem now. All right? Oh, give me an eraser. Clear all this stuff out. And now we're coming back and saying, okay, let's figure out y. Before we go on, I now know that sucker is 4. So if I'm going to figure out y now, I'm looking at the relationship. Which two triangles is this a piece of? Y is the hypotenuse for this small blue triangle, and also y is a leg for the overall big triangle. That one length is a piece of two different triangles. I'm going to build my proportion then using the small triangle being similar to the big triangle. And so, starting off with my small triangle in the blue and my big triangle in the yellow, I have to build another proportion. And what I'm looking at in the small triangle, y is the hypotenuse. Hypotenuse has to match hypotenuse. So what is the hypotenuse for the big yellow triangle? Well, that kind of got cut off. That was 9. 9 and 4 together make 13. Hypotenuse matches hypotenuse. And now I'm coming over and looking at that y again and saying, in my yellow triangle, y in the yellow triangle is the shorter leg. Short leg has to match short leg. So, what is the short leg in the blue triangle? That's 4. I built my proportion. Hypotenuse matches hypotenuse. Short leg matches short leg. And because they're similar, I now can solve this proportion. Y times y, 13 times 4 gives me 52. Take my square root. And I have my answer, y is equal to the square root of 52, which does need to be simplified to its simplest radical form. I recognize, of course, because we just did it, 52 is 4 times 13. So that is the square root of 4 times the square root of 13, giving me my answer 2 times the square root of 13 for y. Okay, 2 times the square root of 13, and we've got y. Next, we have to get z. And so I've got to clear all of this stuff out, and we have another choice. We can do this a third time. If we choose to do it a third time, z is the hypotenuse for the medium-sized triangle. And so we can say hypotenuse matches hypotenuse. For the overall big triangle, z is the longer leg. So we can build it long leg matching long leg. Long leg matching long leg. We can solve this proportion and we'll get our answer. Absolutely valid, completely correct way. It's actually the method that I prefer because I saw how quickly I could build the proportion. This just tells me z squared equals 9 times 13. I take that square root. I got my answer right there. The square root of 9 is 3, square root of 13, root of 13. And I'm done. This is my preferred method. But I do want to point out, of course, come on, give me my purple. We have a hypotenuse. We have a leg. If you wanted to, we could have just used Pythagorean theorem. After we got x and y, then we had two sides of a right triangle. We could have used Pythagorean theorem to get that answer for z. I prefer the proportion, simply because, I don't know, I'm already doing it. I've already done it twice. Why not just do it a third time? It's not any more difficult, and I'm already, I guess for me, it feels like I'm already in a groove with that technique. And so it seems simpler to use the technique a third time rather than switching techniques. Not everyone will feel the same way I do. That's okay. You can pick the technique that you want. All right, and here's our last example for the day. How tall is this Douglas fir? That's all the problem is. How tall is this tree? So you've got a surveyor who basically sets themselves up to create this picture where we know we've got the 90. We know that we've got a 90. So it fits our picture. Well, again, you've got the choice. Do you have the equation memorized, or do you build the proportion? The equation said h squared equals x times y. If you have that equation memorized and you have it memorized where they go in the drawing, we could simply look at this and say 7.8 squared equals 1.6 times y. Okay, 7.8 times 7.8. Pull up our calculator. 7.8 times 7.8. 60.84. Okay, 60.84 equals 1.6 times y. Of course, after that, we have to divide by 1.6. So divide by 1.6. And that's 38. Rounding it to the nearest whole meter, we've got 38.025. That is not the height of the tree. That is just here. We'd still have to add on that last 1.6 to get 39.625. Rounding that to the nearest whole meter. Come on, stop glitching on me. There we go. The tree is approximately 40 meters tall. We're done. Memorizing the equation can be a valid technique. If you did not want to memorize the equation, we could have looked at the triangle and said, small triangle, medium triangle, and using these two similar triangles, we could have matched it up to build a proportion. Building the proportion when we cross multiply would have given us this equation anyway. Whether you choose to focus your efforts on knowing how to build the proportions by identifying these similar figures, or you choose to memorize a bunch of information, whichever technique you prefer, we still expect in the end that you'll be able to meet the objectives of calculating the geometric mean from a proportion. And absolutely, we expect that you'll be able to figure out these lengths based on this picture, whichever technique you choose to use.